All right. I don't know what music is playing right now. This is some free YouTube stuff. This is stupid. Oh, I mean, this stuff is stupid. Alright. Doing a 1025 quiz 2 review session starting at 4:30. Alright. How's the camera doing? Looks normal. Alrighty. Alright, Bobby. Stand up and stretch and dance. And play. And play. Now you're being a turn. What are you doing? You wanna play? You wanna play? You play? Come. Trying to get my dog on camera. He's just sitting on the ground, not doing anything. Yeah, Bubba. I promise there's a dog here. There he is. Oh, can you see him? I don't know. There we go. Of course this froze. Why is it freezing on me, man? Of course that's super cursed how it got frozen. Let me try to fix my webcam. Keeps doing this. This will not do. Man, I need to fix this. Sorry for the technical difficulties. Man. Alright. Let's figure this out. Trying to fix my webcam here before 4:30. I don't even remember how to do that. Good night. Okay. Shout out Samurai Fun for following. Alright. Sorry for this music. This is like the goofiest stuff. Oh yeah. Just wanted to put some like silly music on. Alright, let's do a webcam. Add source. Not necessarily this one. Fine. Where's this cord, bro? This is this cord. Why is it frozen? It's so stupid. Oh my gosh. Alright, I'm gonna try the webcam the whack way I used to do it on like Zoom. If this is gonna play games with me like this. Oh wait, I can add the... Hold up. I think I used to do it on here. There we go, look at that. Aim down. Oh, okay, yeah. Why didn't I do that before, huh? Alright. So we got this, and we're gonna do this. It's 4:29. We beat the clock, beat the odds. Gotta get this up. We'll put this here. That's how I used to do it. I forgot. Okay. I had my like webcam freeze the other day, and I couldn't figure out what the heck was going on. All right. Shout out to the 2 people watching right now. Y'all are in for a treat. It is 4:30. So I'm going to start a little Math 1025 Quiz 2 review right now. Get rid of that. Get rid of this. Hope this stuff runs smoothly. If you have any questions during this, let me know. Today, we're going to be going over some topics involving ratios, concave up, concave down, increasing versus decreasing rate of change or slopes, and log plots or log versus exponential forms. So basically what I've done today is just gathered a few problems that you might see on quiz 2 this week, and yeah, I'm basically just going to work through them while kind of teaching general topics along the way, I guess, and just giving you like extra tidbits of information. All of these are all these questions I have like full individual videos for, so this is just going to be a whole just a single session where I cover like a lot of those problems, and just maybe I add extra important information along the way. All right, let's get started. So in this problem, they say you've been asked to analyze the following data. We have time, we have variable A and B, and they say which of the following are true. And they're asking mainly about the ratios of A over B for all of these. And so what might help first is to go ahead and find the ratios for all of these time values, right? So for 1, 2, 3, and 4, what I'm going to do is separately calculate the ratios for A over B. So the ratio A over B literally means we are just going to take the values of A and divide them by the values of B. So I'll start off dividing 46 divided by 26. So 46.33 divided by 26.97. I get about 1.7. I'm just going to do this across the board here. So 108 divided by this, negative 4.63. So 108.17 divided by 4.63 with a negative, we get about 23, negative 23.4. We're going to keep going here. We have 181 divided by negative 7. 181.52 divided by 7.77 with a negative. We get about negative 23.36, so negative 23.4 as well. And then the last one, 34.92 divided by 23.5, and we get about 1.48, so about 1.5-ish. Anyway, all right, so number 1, they say the ratio A over B decreases over the interval 3 to 4. So from 3 to 4, we're going from, it's a little sloppy, sorry. This is a negative 23.4, and it's going up to 1.5. So the value is increasing from 3 to 4. So to say it decreases is false. Number 2, ratio A over B decreases over the interval 1 to 2. So from 1 to 2, it's going from 1.7 to a negative value. So that is a decrease in value. Number 3, the ratio A over B does not change from 2 to 3. Now from 2 to 3, we're going from negative 23.4 to negative 23.4, so that is a true statement. The ratio is not changing. So in this case, we're looking for 2 and 3 to be correct. Hope that makes sense. If you have questions, let me know, but otherwise, I'm going to keep rolling. I want to try to get through, I think I have like 14 types of problems within the hour, so by 5:30. Excuse me. All right. Let's jump into this one. They say a function f satisfies the following conditions. We have the curve is bending down, the curve is bending up, and f is increasing for x less than 1. Now, you'll notice I kind of left off reading the last parts of those first 2 statements because they're somewhat negligible. The reason they're negligible is that you can almost assume they're like describing how the graph is changing from left to right. So what I mean is the first statement is describing the left side of the graph, or x values less than 1, and then the second statement is describing the right side of the graph. So from left to right, the function should change from bending down to bending up. Bending down is another way of saying concave down, which we'll talk about during random problems this session. So concave down or bending down is like a downward shape U curve, where concave up will be the flip. It'll be an upward shape U curve. So we're looking for a curve that starts concave down and switches to concave up from left to right. So starting with that, looking at option A, we can see this kind of start here, and even if it doesn't have the entire curve, like the up then the down, or for concave up, down then the up, we can still identify a curve as concave up or down even with just a portion of it. So what I mean is, like with A, this first half here, if it kept going in this same kind of pattern, we could see that it would be concave down. And so we can say that this sliver is concave down. Likewise, with B, this has a concave down behavior if we extend it in the opposite direction. And so both A and B start concave down or bending down. Now, for C and D, they're both starting concave up, because we can kind of see that open U-shaped curve in both of those right off the start. And so if we're looking for the curve that starts concave down, we can eliminate options C and D. Now, for statement number 3, they tell us that f is increasing for x values less than 1. Again, even with this one, I think we can safely ignore the inequality. So we can really just look for between A and B, which of those are increasing, which function is increasing. To be increasing means that the y values are increasing from left to right, or as x values go from left to right. Yeah, so the increasing function of the two must be option A, because B is a very decreasing function. And that's pretty much it. It's a little rough. I hope that makes sense, though. Bending down is concave down, bending up is concave up. Increasing is another way of saying positive slope, or increasing y values from left to right. And if it said decreasing, that would be, the y values are decreasing from left to right. All right, let's keep rolling. I'll go back and number these real quick. This was number 1. This is number 2. This is number 3. In number 3, they give us this function defined by the following graph, f, and they're asking about intervals of x values for which this function is increasing or decreasing. So again, increasing, positive slope, decreasing, negative slope. So we're just, considering the intervals that it's increasing or decreasing. Let's just start with A here, and then I might just jump to what the correct answer is. Yeah, we might do that just to save time. So in A, they say it's neither strictly increasing nor strictly decreasing over the interval 5 to 6. Very wordy. Let's start with this. 5 to 6, they're talking about the interval from 5 to 6. So looking at that graph there, from 5 to 6, we can see that that curve is decreasing. You could say it's strictly decreasing because it is only decreasing. It's not increasing at any point from 5 to 6. So right away, this statement is false because it's decreasing the entire time. What we would look for if neither strictly increasing nor strictly decreasing were true would be an interval like 4 to 5. Because from 4 to 5, we can see that it starts just increasing still, and then it changes to decreasing. So it's neither strictly increasing, it's not just increasing the whole time, nor is it decreasing the whole time, but there is a change from one to the other. That's what you would be looking for that statement. Now, because this first statement of A was already false, then A cannot be true, and then we'd move on to the next question, or the next option, right? So I think the correct answer was D for this one. Let's talk about why. Starting with the first statement, they say increasing over the interval 7 to 8. So from 7 to 8, we can see that this curve is definitely going up from left to right. So that is a true statement. Number 2, decreasing 5 to 6. 5 to 6, we said before, was decreasing from left to right. That is a true statement. Number 3, neither strictly increasing nor decreasing over the interval 8 to 9. 8 to 9. Now here's a very tricky one. They try to trick you on ones like these because we see that for the majority of the function from 8 to 9, it is increasing. But right at the end there's a little turnaround, and it just barely changes to decreasing right before it hits x equals 9. And what that means is it's neither strictly increasing nor decreasing on that interval from 8 to 9. So D becomes our answer because of that. All right, hope that makes sense. Let's keep on to something a little more engaging. So with this problem, they give us a bunch of graphs with 3 data points and a line drawn through each of them, and they say which of these they ask which of these graphs could actually represent a linear function. So you'll notice all of these look linear. They look like graphs of lines, but you'll notice differences in their y values here. I think all their x values are the same, which is helpful, but the y values are all different. And what we're looking for to, in order to prove that one of these is a linear function, we want to show that one of these has a constant slope the entire time. So a constant slope meaning it just has the same slope, the same rise over run the entire time. You could think about it as rise over run, or if you prefer solving things algebraically, you could think about it as the slope formula, the change in y, y2 minus y1, over change in x, x2 minus x1. There's a bunch of different ways you could go about it. Personally, I prefer rise over run, so I'm going to talk about that. So just checking A through D, checking their rises over runs, let's demonstrate it with option A first. So from this point to this point, there is a rise from 11 to 17, a rise of 6, and a run from 6 to 8. So a run of 2. So 6 over 2 is a slope of 3. So what that means is the slope between these first 2 points is 3. Then we find the slope between these 2 points, the second and third point. And what that looks like is there's a rise from 17 to 19, so a rise of 2, and a run of 8 to 9, so a run of 1. And so 2 divided by 1, or rise over run, equals 2 over 1, and 2 over 1 is equivalent to 2. So we would ask ourselves, is the slope between these first 2 points equal to the slope between second and third point? And they are not equal. So 3 does not equal 2. So we would eliminate that because that does not have a constant slope, and we'd move on to the next one. And so you can kind of get faster with these as we go along. So first 2 points, we have a rise of 3 from 7 to 10, and a run of 2 from 6 to 8. Second and third points, rise of 2 from 10 to 12, and a run of 1 from 8 to 9. Again, 3 halves does not equal 2 over 1, and we move on to C, so we eliminate B. C, we have a rise from here to here, a rise of 2 from 7 to 9, a run of 2 from 6 to 8, and we're checking to see that the slope of the second and third points, second and third points, we have a rise of 1 from 9 to 10, and a run of 1 from 8 to 9. And we're checking to see, does 2 over 2 equal 1 over 1? And it does, because they both equal 1. So C would be our answer here, because the slope between the first 2 points equals the slope between the second and third points. And then just to disprove this one, first 2 points has a rise of 10, run of 2, and second and third points, rise of 6 from 37 to 43, and a run of 1. So 5 over 2 is not equivalent to 6 over 1. All right. Very, long one there, but I hope that makes some sense. We're just checking slopes. Here's maybe an intimidating one, but I promise it is not too bad. They give us an exponential equation, and they say which of the following is the logarithmic form of this equation. The way I like to do it is basically just get rid of the e. So if we're starting with this equation, e to the 3x plus 4 is equal to 6, we want to eliminate the E term. The way we can eliminate E is by introducing natural log, or taking the natural log of both sides. When we take the natural log of an E term, natural log and E cancel, and we're left with whatever was in the exponent's place. So 3x plus 4 is equal to the natural log of 6, and if we just flip-flop these, we will find our answer in C. And that's all there is to it. So you could almost like not worry about the actual like solution process. Really, if you just saw 3x plus 4 somewhere in your answer, and you saw a 6 somewhere in your answer like that, you could probably identify it pretty easily like that, kind of in a shortcut way. But ln and E will always cancel each other out. They're inverses of one another, and that is what they do. All right. Number 6. Excuse me. All right. They say, suppose that you know that the mass of a bacteria culture grows exponentially. Use log plots to determine how fast the bacteria grows. So there's a big lesson in this whole section about like bacteria mass populations that are growing exponentially, right? Let me do it down here. So bacteria mass, BM, is always growing exponentially. It has that curvature to its growth of its population, whatever. And then the lesson, the whole idea is if we were to take the natural log, it's almost like we're logifying the bacteria mass values. If we take the natural log of these curved exponential values, what happens is it sort of translates what was once an exponential curve into a now linear function. So not a linear curve, but a linear function. It turns it into a line. The importance of this is that a line you can find the rate of change of pretty easily. You can find the slope of a line pretty easily. And so if they're asking about the growth rate, they are talking about, hey Emma, thanks for joining the membership and being able to watch these videos. That's great. Good deal. I don't know if she's like in here. I don't know how that works, but it popped up on here, so that's pretty fun. All right. So the idea with this is because they give us the bacteria mass values, what we want to do is take the natural log of these bacteria mass values. So I might even try to squeeze it in here. ln of bacteria mass. So adding just another section to this chart, right? And I'm going to write out what the ln values of these bacteria mass values are. So we're finding natural log of these values. You could do this in Desmos, you could do this in Excel. I might demonstrate it in Excel real quick just because that's applicable. Alright, so let's see if we can view this together here and get out of here. Alright, so what I'm going to do is find the ln, the natural log of these bacteria mass values here. So if we have, I might just do everything in Excel here at this point. So let's go ahead and just kind of input this data here just real quick. We'll do BM for bacteria mass. We'll do 437 and we'll do 797. And down here we'll do what we're calling the ln of bacteria mass. All right, so in this ln of bacteria mass row, we're going to actually take the ln by typing equals ln and then whatever number we're trying to take the natural log of. So we can just click on that in Excel. That's pretty fun. We hit enter. This is the natural log of this bacteria mass value. The nice thing is that because this referenced the cell B2, we can click on this corner and drag it across. And what this does is automatically find the ln of C2. See how it applies to that 797? That's pretty cool. So we have the ln of both of these values. Now, because we have the ln of both these values now, keep in mind, taking the ln of bacteria mass values turned the exponential curve into a linear function, which means with a line, the equation of a line, we can find the rise over run, or the slope between these 2 points, in order to find the growth rate. So what we're going to do now is find the basically the slope, like y2 minus y1. So y2 minus y1 over x2 minus x1. We're going to find the slope between these 2 points, but using these values with these time values. These time values are like the x values, if you will. So I'm just going to input that on Excel so you can see it right here. So to find the slope, or the rate of change, we're going to do equals. In parentheses, I'm going to do y2 minus y1. Again, this is y2 minus y1. Close parentheses. We're dividing this by the change in x values, x2 minus x1, so 3 minus 1. Oh, shoot. I guess we could do 3 minus c2, sorry, c, whatever that is, c1 minus b1. There we go. We want to just reference all those cells each time. Anyway, long-winded way of saying we get 0.3 for our slope, or our rate of change. And we're just looking for that 0.3 somewhere in the answer. So that gives us option A as our answer. All right. So this really was like a long explanation to say, if you wanted to, right from the start, if you have a good calculator that has the ln button on it, you could even just do like ln of 797 minus ln of 437, all divided by 3 minus 1. That's exactly what we just calculated to get 0.3. All right. Lots of backstory in that last one, so let's pick up the pace here. This is number 7. We are roughly halfway through, and we're not even halfway through the time. We're doing great. All right, so in this one, they, again, tell us that the bacteria culture grows exponentially using log plots, which of the following best estimates the data in this chart. Now you'll notice they gave us the hours just like the last time, but now they're actually giving us the ln of the bacteria mass values. That's pretty fun, right? So we don't have to actually find the ln of those values on our own, but actually we have to work backwards and find what the bacteria mass, the regular bacteria mass function, could have been. And so here's kind of the way we'll do this. We'll still actually find the slope between these 2 points. And the nice thing is, since they've already taken the ln for us, we don't need to do that before we find the slope. So we're just doing slope first. So y2 minus y1 over x2 minus x1, where 11.398 is our y2, 9.598 is our y1, and we do x2 minus x1, or the difference in the hours. So I'm lazy, so I'm just going to do that in my phone real quick. We're going to do 11.398 minus 9.598. Yeah. And we get 1.8 on top, and 5 minus 3 on the bottom is 2. 1.8 divided by 2 is 0.9. Now, what is the significance of this 0.9? This 0.9 is the slope of the log plot, right? It's the slope of the ln plot. And how does that translate to just the exponential, like the regular bacteria mass function? That 0.9 you should find in the exponent of an e term. So we should see an e to the 0.9t in our function that we're looking for. So right away, once we see that or identify that, we can eliminate pretty much every single other answer. And now we're left with either C or G. So now the easy way to go about checking which one of these is correct is really just to like plug and chug one of the time values that we see in our chart here. So let me talk through a little bit more what I mean. We can plug in the hour 3 into option C here. So we're going to test out 90 e to the 0.9 times 3. What this will give us is the bacteria mass value at time 3. So bacteria mass value at t equals 3. So let's go ahead and calculate that real quick. Might demonstrate doing that in Excel real quick. Why not? Kind of give some Excel literacy lessons here. So we're going to do equals 90 times, now where you're doing e to the 0.9 times 3, the e function is exp, and then whatever's in the exponent place we put in parentheses. So there's no need to like use a caret for the exponent, you just put whatever's in the exponent in parentheses next to exp. So 0.9 times 3, and we close that off and we hit enter, and that should give us the value of the bacteria mass at time 3. So we have about 1339.176. Sorry, I'm a little sloppy here. So that is the bacteria mass value. So it's important that I keep pointing out that this is just the bacteria mass value. So like this automatically will never match up to this value here. But what we want to do next is to take the ln of that value, because keep in mind in the chart they don't just have bacteria mass value, they have the ln of the bacteria mass value. So we're going to plug in, we're going to take the ln of this value we just got and see if that matches the ln of the bacteria mass value that we had in the chart. So we can use Excel again, looking at Excel over here. Taking the ln, we hit equals capital LN and parentheses, and we can just tap on that cell, and that's taking the natural log of that value, and we get about 7.199. And when we do that, or like, so we get 7.199, we are comparing this value to this value, and right away we can see that it does not match 9.598. So it does not match 9.598. So it means that C cannot be our answer, and G must be our answer. So that's pretty much it in terms of process of elimination. If you wanted to really confirm that G was our answer, of course you could plug 3 into this function, find that value, then take the ln of that value and confirm that it equals 9.598. I'm not going to do that. Probably done it in another video already, and running low on time. So I'm going to go on to the next one. We're going to call this number 8. And I think this is actually like the same exact problem. So let's check this out. Same problem, different format. They give us the line version. So see how they have like the ln of y. ln of y is representing this function here, just like ln of bacteria mass was representing this line in that little sketch I did earlier, right? So they give us ln of y, and they give us a couple ordered pairs on this line here. And so because this is a somewhat linear function, again, it's a log, like linear log plot function, we can just start the same way we did in the last one by finding the slope between the 2 points that they give us, because it's already in the equation, or in the form of a line with the ln of y function. It's not an exponential curve. So we're going to do y2 minus y1, 1.191 minus 0.435 over x2 minus x1, or t2 minus t1, so 3.9 minus 0.3. And we're just going to calculate that. I'll just use my phone again. Too lazy to juggle Excel for this. 1.191 minus 0.435. We get 0.756, and we're dividing that by 3.6. We get 0.21. So 0.21 as our slope of that log plot line. And that slope, again, will show up in the e function, in the exponent of the e term next to a t. So we should see an e to the 0.21t in our answer, and it should be positive. If we had gotten a negative value here, then it would have been negative. But in this case, we only see one answer with a positive 0.21t in the e exponent, and that is option B. So we are done. If there were multiple answers that had 0.21t, we would do the same approach as the last one, where we would plug and chug different t values. So, for example, we would plug in 0.3 into this function, and then we would take, so we would get that value once we plug in that 0.3, then we would take the ln of that result and then see, does that match the 0.435 we see as the y value there? Because keep in mind, these are the ln of the y values. So like this is the y value, this is the ln of the y value that should match that y value in the ordered pair. All right, hope that makes sense. A little crazy, but got the steps here if you need to play them back. All right, that was number 8, I think. Yeah, I guess so. Number 8. Let's do number 9. Doing great on time. Might take a little water break. Make sure to stretch and not hunch over like a shrimp. Too much math will do that to you. All right. Which of the following, or using the following table of data about a population, determine the greatest rate of change of population? All right. Biggest lesson, rate of change. Throughout this whole semester, rate of change is just a phrase that means slope. So all they're saying is determine the greatest slope of population. In other words, the most positive slope. So how do we indicate the most positive slope of the population? Well, if these are the p-values here, a positive slope, we mentioned earlier, indicates that the function must be increasing, which means the population values must be increasing from left to right in order for the slope to be positive, or the rate of change to be positive. So if we are looking for the greatest rate of change, or the most positive slope, we first of all want to eliminate any, I guess, like intervals that have negative slopes or decreasing population values. So what I mean is, as we scan through these values, these p-values from left to right, we're gonna like ignore any decreasing population intervals. So starting here to here, the population value decreases from 4 to 1. So that would have a negative slope between those two values. So we can basically eliminate that and keep going. From 1.35 to 0.91, that is a decrease. So we eliminate that. From 0.91 to 1.08, that is an increase. So we would keep that. 1.08 increases to 2.41. That's a positive slope. We'd keep that. 2.41 increases to 4.6. We'd keep that. And finally, 4.6 decreases to 3.46. So we can eliminate that because that is an interval of decrease. So what we need to do is actually find the slope. Find 3 different slopes. One of them between these two values, one slope between these two values, and one slope between these two values. So each of these little intervals here. So I'll call this 1, 2, and 3, and I'm gonna label them down here. Yeah, let's do that. All right, so find the first slope. It's gonna be a very tedious process here. 1.08 minus 0.91, all divided by 4.9 minus 4.7. As you can tell, the y2 minus y1 corresponds to the population values, and the x values are the t values, right? So I'll just set up each of these and then I'll calculate all of them at once. Let's keep going. So number 2 would be the interval from 4.9 to 6, so it'd be 2.41 minus 1.08, all divided by 6 minus 4.9. And the last one, number 3, is 4.6 minus 2.41, all divided by 8.3 minus 6. All right. Super fun stuff. Let's just calculate this on my phone. Do 1.08 minus 0.91. We get 0.17, and we're dividing by 0.2. And we get about 0.85. So also to just generalize what I'm doing here. We're finding all three of these positive slopes, and our goal is to find the greatest or the most positive slope. So we're finding the most positive slope, most positive slope of these three. Okay, 2.41 minus 1.08, we get 1.33, and we're dividing that by 6 minus 4.9, which is 1.1. So we get about 1.21. And the last one, 4.6 minus 2.41 is 2.19 divided by 2.3, 8.3 minus 6. So we get about 0.95. So long, tedious way of just saying that 1.21 is definitely the most positive slope of these three. And so that should be our answer. Hope that makes sense. Let's keep going. That was number 9. This is number 10. They say the following table of data provides the biomass in grams produced by the red seaweed, whatever this says. They give us basically just a chart of day and biomass values. Your lab partner used average rates of change to describe behavior in the biomass over 3 stages between day 14 and day 50. Which of their descriptions are correct? And they're asking about like different stages and by how like much they're increasing or decreasing by, like at what rate increase most rapidly, like a bunch of stuff like that. So let's talk about what they're asking about, I guess. They first mention average rates of change. Again, rates of change indicates the slope of something. Sometimes it's the slope at one point, like you'll learn later about derivatives. But in this case, if they're specifically saying average rates of change, average rate of change is another way to describe the slope between 2 points. So slope, how we usually know it. So slope is typically between 2 points. So if we're finding the slope between 2 points over 3 stages, we have the first stage, second stage, and the third stage. Just like in the last one, we'll have like a 1, 2, and 3, and then we'll answer these questions, true or false, kind of relating the slopes in these different stages. All right, so again, we'll do a 1, a 2, and a 3, and we're finding slopes. So we're doing just y2 minus y1 over x2 minus x1. I'm going to set all these up and then I'll calculate them. So then 170.8 minus 149.2, 48 minus 44, and the last one, 172 minus 170.8 over 50 minus 48. All right, again, I'll just do this on my phone real quick. Hopefully I wrote all those out correctly. Shout out to the one person who's determined to crush this quiz, who's still sticking it out with me in here. So we have 72 on top here. I'm just going to calculate everything and then say what the slope is. So we have 72 divided by 44 minus 14, which is 30. So divided by 30, we get about 2.4. All right, next one, 170.8 minus 149.2 is 21.6, and we divide that by 4. We get 5.4. And the last one, 172 minus 170.8. Let me try that again. 172 minus 170.8. Then we divide that by 2. So we get 0.6. All right, hopefully I did all those right. So now that we have these values, again, these are like for the different stages, stage 1, 2, and 3 that they're referring to. Starting with statement 1, they say the biomass increased most rapidly during stage 1. Most rapidly would mean that we're looking for the most positive or the highest slope that we calculated. So they're saying that stage 1 has the highest slope, which is not true. It's 2.4, where the highest is actually 5.4. So this is a false statement. Number 2. During stage 2, the biomass increased at a faster rate than during stage 1. And that is true. That's what we said just a second ago. Stage 2, it increased at 5.4, which is a faster rate of change than stage 1, which had 2.4. Hope I said that right. Might have said, I don't know. Let's go on to number 3. They say during stage 3, the biomass increased at a slower rate than during stage 2. And that is correct, because during stage 3, it was 0.6, and that is a slower rate than 5.4, which we had at stage 2. So I believe 2 and 3 are correct here. And that's all there is to it. So find the slope between each of those pairs of values and compare them based on the statements and identify whether they're true or false. Looking at number 11, I mean. We have, I think, 4 more. 1, 2, 3, 3, 4, including both those. Okay, we're doing great. So, number 11. They say, using the following plot about population, determine the greatest rate of change. Again, greatest rate of change means the most positive slope. So most positive slope, it's a little easier to see it with this problem, because if they're asking for the most positive slope, we can really look for like the steepest increasing part of this function. So any intervals that have decreasing parts of the function, like at the start here, we can ignore. So we're not concerned with any decreasing segments. But as we look at all the increasing segments, we can probably eliminate things visually. So just by looking at these, we can probably tell which one's steeper, or the like more steep than the others, I guess. So let's start by comparing 2 lines here. If we compare this line with this line, we can hopefully see that this line definitely has a steeper slope than this one down here. So we can eliminate this one, because our goal is finding the most positive, or the greatest most steep slope, right? Now, comparing this one with this one, I still feel like this line here starts off pretty steep, whereas the second one, it like just barely like bends down, like gets a little less steep, and so and onward, like so. So I think we can eliminate those top 2 there. So we can narrow it down visually by finding the steepest positive slope. And then they actually have values here. So the idea is to try to identify first what these ordered pairs are that create this segment. In other words, the x and y values, and then actually calculate the slope between those 2 points, y2 minus y1 over x2 minus x1. So it takes a lot of estimation here, so really just do the best you can. Let's see if we can give it a good shot. I'm going to get rid of this so it's not cluttering this. So we're looking for this point here. It looks like an x value of maybe, good night here, let's see. Just see the point here. That's like just under 7, so maybe 6.9. And the y value is just above the line, y equals 2, maybe a little more than just above, so maybe like 2.2. All right, a little sloppy, but hopefully makes sense so far. Then we're looking at this point here, which is just past like 8.5, so it's maybe, I'd say it's a little more than just past, so it might be 8.7. 8.7 for the x value, and then it's definitely just above that y value of 4. So I'm going to call that 4.1 as an estimate. And now that we have the ordered pairs, again, we're just finding the slope between these 2 points. So I'll start with the 4.1 minus 2.2 and divide that by 8.7 minus 6.9. Make sure that your ordered pairs are like corresponding over top and bottom each other. Otherwise, you might get a wrong answer. All right, so 4.1 minus 2.2, we get 1.9, and we're dividing that by, let me write that out, 1.9, and then I'll do 8.7 minus 6.9, we get 1.8. 1.9 divided by 1.8 gives us 1.05, repeating. So about 1.056. So if we had to round that to something, I think our best bet is this 1.1 here. So if we round it to 1 decimal place, that 0.5 would round up to 1.1. Hope that makes sense. So find the steepest line, identify the ordered pairs of its segment, and find the slope between those 2 points. Here's a fun one. Number 12. Here, they give us the plot of a biomass function, plot of a biomass of a fungus. Find the plot that best describes the rate of change of the biomass. So they're giving us an original function, the biomass, right? Then they're asking which of these graphs down here describes the rate of change of this original function. Again, rate of change is describing, or is just another phrase for the slope. So they're asking us to basically like analyze the slopes and see which of these graphs could represent the slopes of the original graph. Okay, so let's talk about how we can do this. With the original graph, it'll help first to identify where does this graph have a positive slope and where does it have a negative slope. So right off the bat, between, I was about to say 0 to 2, but I think it's even less than that. I would say just for this first like segment, really like just this little first segment here is where we have a positive slope. So I'll say positive for that. Positive slope. And then I would say even right after that, it's hard to tell. It looks almost flat at that next segment here, but I might even say it turns negative from here all the way down. So we have like a decreasing slope or negative, or decreasing function or negative slope the rest of the way down. So just like highlight it, I don't know. So negative slope the rest of the way down. What we're looking for is wherever this function has a positive slope, we should see positive y values on the rate of change graph. I'll say that again. Wherever this graph has a positive slope, this graph should have positive y values. So increasing biomass, I'll just say increasing BM equals positive y value for the rate of change. Likewise, wherever the biomass original function is decreasing, so decreasing biomass, we should have negative y values on the rate of change graph. So let's see if we can use this to eliminate some options here. Right off the bat, we have this positive slope, that one little slice, the one little sliver, up until about t equals 1. So from time 0 to time 1, we have a positive slope, which means on the rate of change graph from about 0 to 1, we should have a positive y value. Okay, so scanning through these, A looks like a reasonable option. Let's keep going through. On B, it starts off negative. So right away, that can't be the answer, because if this is starting off with a positive slope, the original function starts off with a positive slope, then the rate of change should start with positive y values. So we can eliminate option B. Likewise with C, it starts below the x-axis. It starts with negative y values, so this is out of here. And then for D, we have that this curve from the start does start above, and it's staying positive y values until after 2. Now, the after 2, see how it's like to the right of 2? That's important here, because we can see that graphs A and D look very similar, but the only difference is where they cross the x-axis. And so if we were saying that this function looks like it's only positive from about 0 to 1, and then it changes to negative, then this should kind of be the key for where the rate of change graph should have positive values and then negative values. So what I'm saying is, to say that it changes after 2, like to the right of 2, feels wrong. I don't think that's the right idea. I think because this function changed from positive to negative slopes, I would say before 2, we're saying right around 1, then I think our best bet is option A. And that is our answer. All right. Again, that's probably one of the harder ones, to be honest. It's a little tricky. I wouldn't sweat it too much if it's stressing you out. It's going to be kind of a practiced thing over this semester. We'll see more problems kind of like this. Honestly, this is a tricky one to be thrown in this first section. If it's stressing you out too much, I wouldn't put too much energy into it. I would just try to focus on the other ones. But I hope this helped a little bit. Again, I have other videos on this one if you need help. All right, let's end on a nice and easy one, referencing what we did back in the beginning of this session. We briefly mentioned concave up and concave down. Concave up, you can remember because the word up has an uppercase U, and an uppercase U looks like a concave up curve. So concave up looks like this, and concave down is the flip, right? And so in this first question, they just say, choose the correct description of concavity, concave up or concave down, for the following graph. So looking at this graph here, we want to know, is it concave up? Is it concave down? Is it a little of both? Yeah. So I would just start with like what you can say with certainty. So it's probably easier, I think, to look at this section and say that that definitely has a concave down behavior, right? So right over here, we can say it's concave down, CCD, which means if it's concave down here, then there's kind of something different going on over here, right? We could probably say that this is concave up. And it's a little less obvious, but I think it's fair to say that you can like kind of see that behavior. You can at least see that sliver of the concave up curve, right? Anyway, hope that makes sense. I hope it's not too complicated. The biggest thing to make sure you do not do is think about it as like increasing and decreasing, because they're totally different things. Concave up literally is like the curvature of it, and concave up and concave down, and then increasing and decreasing is like the y values just going up and going down. Okay, so this one starts concave up and switches to concave down, and the easier one of these two, they say, choose the correct description of concavity, and here we can see that this is textbook concave up for the entire graph. So this graph is only concave up. I hope that makes some sense. All right, I'm going to scroll through just all the problems we worked through today. That was it. Thanks for sticking in there, whoever's in this live session right now. And this will be posted later on if you want to check it out. So what we covered today, a little bit of ratios, concave up, concave down, increasing, decreasing, rates of change or slopes, log plots, yada yada. I'm just going to go through each of these problems. I will be doing these weekly live sessions for the quizzes, every week. But from now on, they will be for members only. So if this was a good time, if you found this beneficial, then I recommend clicking the join button and hitting that weekly study sessions option, and hanging out with me every week. You can send in questions. This is really meant to be a space where you can email me questions or send questions over the Discord server we have. And I can, this is a place where I can work out those specific problems, those questions that you have trouble with during these live sessions. So they're not just, for me to work out problems that I have, but problems that you have, right? So I, recommend if that sounds good to you, take advantage of that. Try to get help each week for a, fraction of the cost it would be to pay a private tutor, right? So I hope this helped. If you have any questions, please let me know.